Afternoon, everyone. My name is Subhabrata Bhattacharya, and I'm here to present my dissertation defense, which is titled as a bottom-up approach towards recognition of complex events in open source videos. So to begin with, what do we mean by complex events? You here see three examples of those. Left one being a birthday party, right one being attempting a boat trick, and the center one is boat trick, and the right one is feeding an animal. So for humans, these depicting what kind of events are there in these videos is not a big problem. But for machines, computer vision, for that matter, has a lot of problems because of the challenges that I list below. As you can see, these events are captured under unconstrained scenarios, which is wild. It has a camera background, jitter, lots of camera motion. There is foreground and background clutter, illumination changes, which are standard computer vision problems. Also, the other thing, in addition to that, is these videos are semantically diverse. What I mean is, a birthday party can happen for a 2-year-old as well as an 80-year-old. And so there is a lot of semantical diversity. And so on follows for a boat trick. A boat trick can be surfboard, skateboard, wakeboard, any kind of boarding event. And so they are semantically very diverse. Now the idea is this, because of this diversity, it is a very hard and challenging problem other than standard action recognition or gesture recognition or any other object recognition, which are sort of in constrained scenarios. Now, why would we want to do recognition of complex events? As we all know that we are in the era of big data, where we have these video sharing websites such as YouTube, Hulu, Flickr, and Vimeo. And so there is a deluge of all these videos coming from different websites. People want to share them. One of the things that if we can do, if we can really recognize complex events depicted in these videos, first thing that would come handy is summarization of these videos for analytical purposes. A lot of intelligence agencies use this. Other thing would be virality prediction of videos, where judging by the content itself, you would be able to tell you whether this video is going to be viral or not. And the third thing is obviously the product promotion, which is based on users' interest. You can track the content they are watching, and then you can promote your products accordingly. So these are the three key motivations of this research. And having said that, there are several earlier approaches that are produced in this direction. So the basic idea here is, given an input video, you extract some features. These are low-level features. And you quantize them according to some vector quantization methods, in which I'm going to elaborate later on. And then once you have that representation, you basically feed it to a classifier and predict what kind of event it is. Now these are under the general umbrella of bag of low-level feature kind of approaches. Now, the good part about them is they are relatively very simple to implement, and they give a good recognition performance over standard data sets and all. The bad part is you don't have any semantic representation of what is going on inside the video. For example, these low-level features cannot express what exactly is meant by a person feeding an animal. So for that matter, there is a parallel work which is on concept-based representation. What happens is you divide a video into certain parts, and you apply some sort of concept detectors. These concepts could be thought of scene-level concepts, where you can see whether it's an outdoor setting or an indoor setting, or it could be like a person running or person jumping, that kind of mid-level concepts. So once you have this concept-based representation, you can feed it to a classifier. And then so on, you can go ahead predicting what kind of event is going on. Good part about that is it is relatively very complex than the bag of low-level feature-based methods. And but that's why there is a lot of room for improvement. But the good part is it provides you good semantic interpretation of what is going on inside the video. So in this research, I formally put that we hypothesize that we want to do a systematic decomposition of a complex event, which is extremely necessary to understand the structure of what is going on inside a video, as well as it will help improving the recognition performance overall. And the third thing that we get as a byproduct is it would facilitate different research novel ideas at different levels of this decomposition. Now, by the decomposition, what I mean is at the lowest level of a complex event hierarchy, what we analyzed is we can think of something called attributes. And these attributes are really low-level attributes, which you can think of as a right arm moving up, left arm moving down. And this, when used together, they can form model and action. For example, waving, person waving. That is one action. These actions, when happen between subject and an object, for example, a subject is turning a wrench. So there are a subject and object involved here. And so these actions can be further thought of as an interaction. So that's the next level of hierarchy. And once you have these different interactions, and these interactions can also be called concepts, what we previously meant. What turns out that you have these different kind of actions or interactions interleaved together in a temporal order, and that is what your complex event. So in here, we have an example of a changing entire event where on the left you see an action such as person squatting, and this is followed by person turning wrench, and then further person closing trunk. So if you can actually detect these concepts happening inside a video, whatever their order is, then you can predict, okay, this is a complex event because I have these sort of evidences supporting what particular underlying event it actually denotes. So what we propose here is contributions at all these intermediate levels, beginning with the low level, and that's how we can improve the ultimate recognition accuracy. So this is what our bottom-up approach is. So what we start off with is design of low-level features, novel features, what we can think of given the problem. This is followed by designing computationally efficient representations, which would be used on top of these features. And once you have this representation, you can analyze the temporal statistics between these intermediate representation to model events. So as per the thesis, these are organized in these chapters. I welcome you all to have a look at it for details, but I'm going to brief through all these sections one at a time. So first comes is the design of low-level features, where we explore two different modalities. One is we think of what kind of global contextual information we can get given a video. And that's the first part I'm going to talk about. Second one is about getting camera motion from the video, and which could be used as another cue for representing an event. So here's the first part. Give you some background on what happens when we use these low-level features. So as you know, there has been a lot of work designed on videos which work with low-level features. There has been dense sampling-based MBH features, interest point detectors, and then there are SIFT 3D, these kind of descriptors which have been used before. Now, the problems with these approaches are detection and the description. The detection part is they have computationally expensive detectors, which would basically find out gradient information throughout a video and then see whichever the gradient is, like hits a peak or something. And that itself is a computationally intensive operation. Also, you have to do lots of filter parameter selection, which is why it's not optimized for certain data sets. And these all approaches are based on a small spatio-temporal neighborhood. That's the detection problem. With description, once you have these features detected, you want to represent that, and that data representation is often very high dimensional, which needs further vector quantization. So, question that we want to ask here is, can we avoid this detection step? And also, can we create a compact descriptor of what is happening in the video? Another problem with the spatio-temporal detector descriptor-based approaches, we are taking here example popular HOG, HOF, which is giving state-of-the-art performance in lots of video analysis problems. So we have, here we show a video of a small event called pizza tossing. So what happens is here you see a pizza being tossed up. So there are these motion components which are shown in the red vectors, and the intensity component shown in the blue vectors. So the way the HOG, HOF works is you concatenate these two different kind of descriptors together, and then you get a final representation for analyzing what is going on. Now the problem with that kind of approach is we lose the relationship between the appearance and intensity, which we find out further that this is really important. So the idea is, how can we efficiently capture this correlation between how the motion is changing with respect to appearance? And hence, we designed this novel descriptor based on covariance matrices, which is compact and it's semi-global in nature. And also, we eliminate the process of vector quantization when we design this. And we can also leverage on the properties of covariance matrices for classification purpose. So now, how we compute this covariance matrix? According to our method, what we do is we first have a single frame. We compute low-level image-based features from that. And that's basically green, blue, and red channel from the RGB data that is available. And also the appearance of information are horizontal and vertical gradients and their derivatives. So this is mathematically represented as this vector, where Fi is your intensity and Fg is the gradient components. Again, features contributing to simple motion. We have pair of consecutive frames. We compute the temporal gradient across them. Also, the horizontal and vertical component of the optical flow. The temporal derivative is also calculated for these two components, u and v. And this can be represented mathematically as this following vector. We also analyze that, okay, in addition to these low-level optical flow or temporal gradient-based features, we can do is we can also compute some local motion features, which is divergence, vorticity, and these are basically inspired by laws of fluid dynamics, where you have flow vectors and you can see what is the local neighborhood of those flow vectors. Are they actually depicting certain complex motion pattern? And also, there are other features that are computed based on optical flow. There is invariant of flow rate tensors and so on. Now, given all these features, features from pixels, we have every pixel in our clip represented in terms of these features, low-level features. What we do is we concatenate them together in one feature vector, and the components are shown like that. Given this clip, given these features, we can compute a covariance matrix. And the covariance matrix computation is pretty easy. Once we have this covariance matrix, we can compute the descriptor. Now, so this slide shows an overview how this covariance is computed. Given a video, we divide it into number of clips. Once we have those clips, compute the covariance. We compute these low-level features, and from those features, we get these covariance matrices corresponding to each clip. Now, what happens here is we have, in this particular example, we show a 19 by 19 covariance matrix. That is because we have 19 low-level features per pixel. And the thing is, since these are symmetric positive definite, we can use just the upper triangular or lower triangular part of it. And we also can leverage on the properties of covariance matrices because these lie on Riemannian manifold. Now, there is one good part of the Riemannian manifold is we have these covariance matrices. They cannot be treated according to the Euclidean geometry. So the reason being, the point you see here in this manifold does not have a valid distance of another point which is on that manifold, a valid Euclidean distance. So for that matter, what we propose is using this tangent space of that Riemannian manifold. What basically does that is you can do an exponential mapping of that matrix, and then from there you can compute the tangent space, and between those tangent space you can have a valid Euclidean Euclidean matrix for computing the distance. And this is computationally done using performing an SVD of the covariance matrix, and then you take the log of the diagonal components of the SVD. Now this particular approach is the simplest approach what you can do, and what it yields is you have these covariance matrices shown in a lower dimensional 3D structure. Once you put them in this, transform them in this vector space, what you see is these different points corresponding to different classes in the covariance matrix space. So there are 8 classes shown. You can see that they are sort of clustering together. So the idea is after this transformation, the classifications becomes much more easy. We also compare our descriptor with the HOG, HOF. Here is a visualization. As you can see, there is a lot of interclass similarity and too many descriptors. Whereas for our proposed descriptors, we see there is much fewer descriptors that we have, and also they are sort of clustered together. Now, once we have that, the next contribution is on sparse coding. Now, the idea here is, given a query matrix, query vector that we have from this transformation, what we want to do is we have a predefined dictionary of these covariance matrices, the vectorized covariance matrices. We want to find out which class these covariance matrices belong to. And so for that, we perform this sparse approximation problem. The idea is to get a sparse coefficient of vectors that would identify which class these matrices belong to. And then there are some good approximation techniques. We use orthogonal matching pursuit algorithm to do this. And the idea is, for different covariance matrices, you can get the minimum residual error, and using that, you can add them up and get a vote, final vote of what particular class of action or what particular class it belongs to. Problem with that approach, however, is it's very simple, and the vectorization kills the matrix structure. As you can see, there is a different structure for different kind of covariance matrices coming from different classes. So for that, what we observe is we can do some sort of tensor sparse coding, where every matrix are treated in their original manifold. And what we do is we perform a sparse approximation based on that. Basically, the idea here is we want to find an approximate matrix which would be represented as a linear combination of all these matrices in our dictionary. And turns out there is a very nice metric for that, which we call the Berg matrix divergence, and that can be used to find these differences between different covariance matrices in their original space. The closed form of the solution can be obtained by this optimization, solving this optimization problem, and there are well-known methods for that. They call the max-state divergence problem. We did some experiments on standard action recognition datasets U2, KTH, actually UC50, KTH, and HMDB51. And the bottom actually shows our results compared to all other methods. We also had some experiments with different kind of variants of our approaches. These all approaches are listed below. And what we want to show here is we incrementally change certain things in our proposed formulation, and we show that definitely it improves over these 3 different data sets. Now we also evaluate what are the different individual feature contributions. So here we show only 8 classes, and as you can see, for this particular class, which is baseball pitch, the intensity-based features matter more, whereas for clean and jerk operation, clean and jerk action, the motion features here contribute more. Again, this ROC curve actually shows the contributions, which features are what, how are they contributing. We also did some experiments on gesture recognition, and here are some sample frames from the gesture recognition data set. This is actually showing one-shot learning, which is a much more complicated problem. Some quantitative results here are shown in terms of these confusion matrices. Ideally, what you want to see is diagonal elements are high values. And so these are our results. With certain other benchmark methods, we also tried. We still perform better than those. And that's what it is showing, that our covariance-based descriptor works pretty well. So as a summary, what we have here so far is a covariance-based matrix based on low-level features, and that can be used to capture contextual information. And there are wide applications for it. We can use it for unconstrained video analysis. We can do it for gesture recognition as well. Let's move on to the next topic on these design of low-level features, and that is cinematographic shot classification, which is basically based on camera motion. So the motivation here behind that is, for certain videos, the camera motion actually captures a lot of information which could be used to predict what is going on inside the video. So here are some examples, and there are some cases where what you can use them for. So traditionally, what you want, how camera motion is computed is you can actually track points in the video, and from those videos you can do traditional structure from motion. But then there are problems with that. It is a computationally very expensive problem, and at the same time you need to do bundle adjustment, which also takes a lot of time. So we propose an alternative representation of camera motion, which is based on homography. And the homographies can be computed between 2 pairs of frames using a point correspondence method. The beauty of this approach is we only have to compute homography between any 2 given pairs at a point of time. Now once we have those homographies, that actually describes some coarse camera motion in a video. So our approach is based on a cinematographic principle, where we basically show how these different videos, aerial and bird eye, here is one comparison. What are the components of the homography matrix that changes? So as you can see, the bottom 2 components for the aerial shot, which has a perspective deformation, that actually changes, whereas for bird eye, those are orthographic. That's why those components remain 0. Similar case is observed for pan and tilt, where the components are shown in red. Those are the changing factors, and analyzing those homography matrices, you can classify what kind of shot it is. Similar with crane and dolly, and also other shots such as establishing and zoom. Establishing is something where camera remains still, and basically these elements remain identity. I'll go now. Once you have these homographies, again, these are projective spaces, so classification here is very difficult. So actually it's next to impossible. So what we observe is we introduce a Lie algebra-based representation of these homographies, which are basically changing these homographies to a geometric space, where a vector space, where you can do classification nicely. So here is the formulation of the vector space, where you have this multiplicative structure of homographies, and which can be actually reduced to this additive structure using this log matrix mapping. And this basically becomes our basis of representations. For this log matrix mapping, you have, for every component in the homography matrix, you have bases, 8 bases for 8 components, and those are denoted by G sub I. So the coefficient corresponding to those bases become our representation. So again, giving an overview, we have a sequence. We compute the interframe homography. Once we have that, we map it to a vector space. And over time, each element in the vector space becomes your time series, an 8-dimensional time series, on which you can compute features and do short classification. So this is here an illustration that shows in projective space how these 4 different shots look like, and in these transformed vector space, how they look like. And the idea is to show that they are more separable. Also, this plot shows how they are separable in the equivalent vector space that we proposed. Now, given these time series, we can compute some features, and we evaluated different techniques based on just statistical measures, then linear dynamical systems point of view, and nonlinear dynamical systems. I won't go into details with that. And we evaluated how these approaches work. So we evaluated that in terms of a newly introduced data set that we created for this purpose, contain 8 classes. And these are some statistics on those 8 data sets. Now, also we evaluated how does computation of homography actually affect. So here you can see what we need is for computation a wide baseline. So this actually illustration shows how you can compute homography between frames and how that actually affects. So what we observe here is for 4 frames, the representation is more optimal than the others. Reason behind that is for closer frames, the homography is much noisier. But for further frames, the vector space representation becomes very noisy because since these homographies are not very close to identity. Finally, we show some results on using the time series. So here on the left, the confusion matrix actually shows without time series what you can get, and with time series what you can get. We see some definite improvement from 65% to 76% here. So we also did some comparison with the state of the art. On the left, you see our method. Actually, on the right, you see our method, and the left are the baselines. The furthest left is basically sort of, you can think of ground truth, where you have the data from structure from motion and how you can use them. This actually also shows the effectiveness of our method compared to the ground truth, which is denoted as a TFT. That's the statistical features computed on XY trajectories if you had them. Now, finally, one last contribution of this method is onto event detection, where you have these 2 different kind of events, making a sandwich versus parrot. And we want to show how the representation of camera can discern between these kind of events. So what we did is, using this vector space representation, we tried to plot them and see how they actually look like. And it turns out that 2 events, boat trek and swing project, shown in green and purple, they look very different in this trajectory space, the vector space, proposed vector space. Similarly, parade versus woodworking project. You can think of woodworking project as being like there's a person, there's no camera motion, absolutely focused towards them, whereas in parade, there's camera panning, tilting, that kind of motion. So these are the trajectory plots that shows that yes, we can do some sort of discrimination based on just the vector space representation that we introduced. Finally, what we do after that is, given a video, we apply these short class detectors, and those are based on these low-level SVM representation that we had. And once you have those short classes, you use a final classifier, which is a hidden Markov model. The idea here is, given a video, divided into these different kind of shots, apply short-level detectors. We used 5 types of short-level detectors here: pan, tilt, zoom, and undetermined and establishing. So that way what we get is a symbol sequence for each of these videos. So each video is now represented using these symbol sequences, and you can use them for training your final HMM-based classifier. And here are some results corresponding to that. This is our proposed method. Basically, the dead curve, the area under the dead curve is what you want to observe is going down. So basically, any curve which has, which is plotted close to this line would be considered really low, and really nice, whereas a curve which is along the diagonal is random. So we perform pretty well compared to methods which use content-based representation. And that's the whole idea, that this can be used as a complementary feature for complex event recognition. As a summary, again, for this approach, we came up with a novel Lie algebra-based representation of camera motion, which could be used as a short-level descriptor, and it can also be used as a complementary feature along other features for complex event recognition. Having said that, now we move to the next topic, which is building a computationally efficient and semantically meaningful intermediate representation on top of these features, which will basically apply for classifiers. Now, traditional way of doing so is the bag of features, as I said. Given a video or image, you find these key points, and then you cluster them to form a vocabulary. Once you have that, basically, given a testing video, you extract those points again, and using some nearest neighbor search, you perform a vector quantization. Basically, you are taking each of those points extracted and putting them to the space of already defined vocabularies, which means some sort of hard clustering. Now, the idea there, and once you have that, you can have a histogram representation. Now, the idea there is that kind of approach is very ambiguous when it comes to points which are in the boundary of 2 clusters. So what we want to propose here is if there exists any other way of improving this representation. So what we have here under proposition is we assume that each of these instances containing different kind of points, data points, they are coming from an unknown distribution over a set of representative points. We won't go into details on how we are selecting the set representative points now, but let's assume that these points are distribution on some characteristic feature points. Now that can be elegantly expressed in terms of this kernel density estimate, where you basically assume that D is your data point, and for each data point, you can find out this probability, how it is generated from an image or an instance using this non-parametric equation. Now, once you have that, the idea here is to find out these weights, which will basically find out what are the characteristic points contribution towards representing these individual data point. Turns out what we can do here is compute a maximum likelihood estimate. And that's the traditional approach to find out what are the parameters for these finding this distribution. Now that can be used, and it looks like this, where you have k as your total number of data points for an instance, and w is your weight, and the capital K is your kernel density function. Now, that having said that, it is a computationally explosive problem, because there could be, depending on the number of characteristic points you choose, this could really be like a 2 to the power k combinations. So what we propose here is a bounded optimization problem, where we assume that the log likelihood is available at the previous step, and what we want to find out, what is the log likelihood at the current step, we take the difference, and using Jensen's inequality for convex function, what we want to do is we want to find out a closed form solution for this particular expression. And the closed form solutions can be expressed in the next slide, which is this. Now, this can be solved using an EM setup, and basically the idea here actually is illustrated in the next slide. We have data points here, C1, C2, and C3 are our anchors. D1 and D2 are our data points. So there are some distances between these data points and the anchors. Now, let's say these distances are represented in that table just below. The traditional bag of words based method would put equal weights to these 2 anchor points out of those 3. This is basically hard clustering. The soft assignment would try to put equal weight for all the characteristic data points, and that distribution would look like that. Our method, in the first step of this EM algorithm, as I said, would look like this. But as we go through different iterations of the method, we would see that C2, which is actually contributing to the representation of both of these data points, is getting more and more weights. So that's the idea, to see how we can, given a set of randomly sampled characteristic points, how we can represent the distribution efficiently. So this final, what we observe is the optimal weight combination for all these characteristic points. Now, there are some other parameters or principles involved in selecting the kernel density function. So here we use a hypersphere kernel, which is just truncating the nearest neighbors across a particular characteristic point. And that can be efficiently done using LSH or FLAN, which are good libraries for nearest neighbor approximation. We can also use a truncated Gaussian kernel, but we experimentally determined that this is roughly gives the same performance as the hypersphere kernel. Here are some experiments on different action recognition dataset. So what you observe here is a KTH action dataset where there are 6 actions, about 598 sequences, 25 actors, and 4 different scenarios. We used a gradient descriptor followed by a PCA to reduce the dimension. And finally, we classify using SVM and linear kernel. What we observe here is the MLE representation that we just proposed based on anchors. The green dots, I don't know if you can see it. We selected at random 500 anchors from about 10,000 data points, and we represented them using our representation that we proposed. And so for every 6 actions in the KTH dataset, these are the representation. Here are some quantitative performance. We do much better than previously proposed approaches. And here is the confusion matrix, where we see some sort of ambiguity between jogging and running, which is kind of expected because features are very similar in those cases. So even traditional bag of words based representation fail there. So I mean, our approach is no bar, because we have to compute features which are really subjective of running and jogging. We also did some experiments on the YouTube action dataset, and here are some sample frames for that. This is a slightly bigger dataset, about 1051 sequences, 10 actors, 10 actions, and there are about 6 actions per clip. Now, total number of data points here is about 350,000, and we did similar setup as we did for the KTA. Here is a confusion matrix that shows some very high performance for certain actions such as the juggling, but and also tennis swinging. We can do this with a very low representation, the very fewer number of characteristic data points as selected as anchors. It's about 20% of the data points. The beauty of this representation is basically you don't have to do clustering. That's one of the good points. This actually plot shows how the optimal number of anchors are selected empirically on different data set. Now we extended this approach to large-scale concept detection, where, as I said, the concept detections are really important for predicting what kind of events. So this actually shows how concept detection is being performed at different modalities, and after that you fuse these to get a final classifier. Some statistics on number of concepts. We have about 93 spatio-temporal concepts, and we apply these detectors in this fashion, where given a video, you basically do a sliding window-based approach and apply these detectors there. What you observe here is we get very high performance for actions such as action concepts such as wheel rotating, and low performance for person surfing. We think this is because of the representative data points. Here is some more quantitative description of what are happening with respect to bag of features-based approaches, and basically you would see the average precision being a higher number than the average area under the curve. So again, we show here that our approach beats the bag of words-based approaches significantly. Since there is 93 concepts, so 2% improvement is also a good benefit. Here are some qualitative results on the correct detection of concepts. And now we go to the summary part, where we introduce the MLE-based representation of an instance, which is very different from bag of words. And we can use random sampling instead of computationally intensive clustering. Other part is, since we are using a large number of support from different data points, the representation is much more efficient. Now we move on to the next part, which is the final part of our event representation. What we propose here is how to get these efficient temporal models based on this low-level underlying concept-based representation. So the idea again here is, given this high-level event or this complex event, changing a tire, we can observe these kind of intermediate concepts. Now what we want to do is represent a video in terms of distribution of these concept detectors. So basically, given a video, you have these different clips, and then for these different clips, what you can think of is a concept detection process evolving over several time frames. And that's what is shown here. The y-axis is the time step, and the z-axis is the concept detection responses. So this graph actually shows how these different concept detectors are computed on different clips. And as you can see, it's evolving. Now what we did was an interesting study on finding the cumulative density function of these concept detector responses. Turns out, for events such as this birthday party, there are two samples here. You can see that concept which is numbered as number 1 here, that shows a very distinctive pattern. Whereas for working on a swing project, the concept which is shown in yellow, it's almost very similar. And we observed this trend for a lot of other samples within the same class. So what we propose is using linear dynamical system-based foundations to find a descriptor on this particular concepts. So the idea here is you assume that each concept vector, denoted as CT, can be represented using an observation matrix, what you directly can observe, and hidden state vector, which is XT, and some noise. This is the classical linear dynamical system formulation. We have a prior X0, which is given for all these concept detectors. Now, since we assume that each detector response is emanated from a slowly evolving process, this kind of representation, this LDS-based representation, is really useful. Now, we cannot actually evaluate these parameters which are represented in this LDS, the parameters being the observation matrix K and the hidden state vector. So what we propose here is using subspace state identification methods, which are popular in indirect estimation of these parameters. So the idea here is we divide this into 2 categories. One is using Hankel matrices. The idea of Hankel matrices is you have a concept vector, which is represented as C0, and you basically stack all your concept detectors in this Topelis pattern. That's how you create the block Hankel matrix. Once you have the block Hankel matrix, you can find the characteristics of the block Hankel matrix based on eigendecomposition. Basically, what you are doing is you have these several set of concept detector responses. You transpose them to their eigenspace representation. And that gives you a good idea of what is happening in terms of the temporal dependencies. One concept, how it differs or correlates with other concepts. After you perform the SVD of the Hankel matrix, you basically reproject it to, let's say, the first or second eigenvectors of that system, and that becomes your descriptor. There are 2 hyperparameters here. One is the overlap, and the other is number of eigenvectors. I have some experiments to show how they actually change. The other part here is the temporal signature, which we also propose on the basis of harmonic grouping. What happens here is these different concept detectors show some sort of harmonic relationship with each other. And the idea is, given these harmonics, you can actually predict what kind of properties they possess. If you do a harmonic decomposition, you would see that the eigenvector, if they are less than 1, then the time series actually shows some sort of exponential decay. If it's greater than 1, then it is an exponential growth. And if the eigenvalues are complex, then it shows some sort of sinusoidal properties of the evolution. Basically, the idea to find out these harmonics is using an SVD of the transition matrix, and which can be expressed in the following equation. Now, the problem again is, since we don't have the transition matrix, we actually applied the state identification method in the other one. Here what we want to do is jointly find this harmonic mixing matrix and the transition matrix using an expectation maximization problem. So basically, the above step you see is the E step, and this is basically the M step. There are a lot of theoretical details involved, which I can show later on. Once that is done, basically you reproject the entire time series into the eigenspace of the transition matrix, and this is how you get the descriptor, which looks like something which you have in the bottom. You can see some sparse components of that, and that is the representation based on concepts. it actually shows certain characteristic properties such as harmonic structure and a lot of lag independence, shift invariance, that kind of properties you can measure from this harmonic matrix. Now we show some discriminative property in these two different feature spaces that we just proposed. One is based on the Hankel matrix, the other one on the temporal signature. Again, the idea here shows that how these 5 different event categories, each dot is a video sample from that particular event, how they are clustered together in these, even this reduced dimensional feature space of these two different features that we proposed. And it actually shows that we can get really some good representation in both of these feature spaces. Now we evaluated that using a few baseline techniques. First one being DCT. Since these are time series data, you can compute DCT features, discrete cosine transform. You can also use hidden Markov models, 2 variants of that, one using discrete, the other using continuous. And these are some baseline performances. Now, we compare those with ours, where these are for 15 different event categories, listed as boat trick, feeding an animal, landing a fish, and so on. And these are our method, HNK and TS. And as you can see, we perform much better than these baselines, beating the hidden discrete and continuous hidden Markov model by a significant margin. Finally, we show some combination, and that also improves the fusion performance. Now, here are some experimental details on how the number of states that you select for formulating this linear dynamical system, how they affect the representation. And you can see this is the optimal trade-off for the temporal signature-based approach. And we can also observe that it is consistent between number of states, not too much difference. What you observe for those baseline methods, those two curves. Also, we did some experiments on the parameter selection for Hankel matrices, and basically the R being the overlap. 2 different trends that we observe for event collection 1, which has 15 different events, event collection 2, 10 events. The accuracy is much lower for EC2. The reason being we have very few concepts that can represent EC2. For EC1, the concept representation is much richer. We also observed that the number of eigenvectors, if we increase, that actually increases the performance quite a bit. Did some parameter selection for the temporal signatures too, but we observed that the simpler the model, it is better. So you don't actually have to increase the complexity of the feature selection process. Some more experiments that shows how these work for these 2 different data sets combined. And we have some failure cases for these different kind of events where we see our representation does not help too much on the baseline, but overall it does fairly good job. Some confusion are being shown here for these 3 different, one actually event class called rock climbing, which is confused with a dog show event and also metal crafts. We don't know very well why that actually happened, but we think again, since these are for these event collection 2, much fewer concept-based representation available for them, that could be one of the reasons. So as a summary, we proposed a novel complex event formulation based on linear dynamical system. Also proposed 2 alternative strategies, how to compute these novel representation. And it does much better than the widely used graphical model-based approaches. Now, as conclusions for this thesis, we started with the ground level. We introduced 2 kinds of complementary features at the lowest level, which can be used for large-scale video analysis. Oh, sorry. Next one is based on this intermediate representation, which can be used on top of these features, and that also improves the classification accuracy quite a bit. Next one is on the temporal dynamics on these intermediate representation space. As part of future work, what we want to propose is using some sort of domain transfer, because what you observed here is already you have training data and you try to do classification based on that training data. What if we did not have any training data? So that can be leveraged using something called a promising direction, which is a stack denoising autoencoder. Here's just a brief of how they work. Basically, you try to learn a joint representation of the data given your unsupervised model. Here are some publications that originated from this effort. And thank you.